Hello all, and welcome to this video where we do a quick refresher on limits and then look at continuity and then use those two ideas to show whether a function is defined as having a derivative or not, or technically if it is differentiable. So let's jump straight in with a quick review of limits. So we've looked at this in units 1 and 2, and we also actually looked at this way at the start of differentiation because we used it when we were differentiating via first principles. Now to solve a limit, we just substitute into the limit, whatever that we are approaching. So in this case, as x approaches 2, we want to find what the limit of that is. And as a quick reminder, we can think of limit as if a graph is a journey, as we are walking along the graph, maybe as we're going from x is equal to 1, as we walk closer and closer and closer to x equals 2, what y value are we getting closer to? And does that happen, maybe this is our function, does that happen, there's x is 2, as we come from both the left-hand side and the right-hand side? Are we approaching the same spot? And if we are approaching and getting closer and closer to that spot, then the limit exists. Now, the easy way to solve these is if that point exists on the function, well, then it's easy just to substitute in to find what that point is. So let's do a couple quick substitutions. So find the limit as x approaches 2. Well, that's going to equal 2. 2 to the 2 to the 4, which is equal to 2 to the 5, which is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Same thing over here. This is going to be equal to 5 negative 2 squared minus 2 by negative 2. And negative 2 squared is 4, times 5 is 20, plus 4 is equal to 24 for that one. This third one, key thing to note is that if we were trying to find the limit when x is equal to negative 4, then we'd have an issue because the denominator becomes 0. So that function isn't defined at that point, but maybe if we could factorize that out and solve for that, then we might find what it is actually approaching. But in this case, we're not trying to find what the limit is x equal to negative 4. We're just trying to find x as x approaches 3. So it's just a matter of a simple substitution. It is equal to 3 plus 1 over 3 plus 4. 3 plus 1 is 4 times 3 is 12 over 7. And that's it. So there's a really quick refresher that we can solve limits just by substituting. Now we get to that example that I talked about, what happens when we're trying to substitute in an x value when it would turn into the function undefined. So what we have to do is first factorize and then simplify, and then we'll be able to do the substitution. And since we haven't done the substitution, we still have to write the limit notation because we haven't done the substitution yet. I can write properly, is equal to now x squared plus 4x. I can just take out a common factor of x, so we get x plus 4, and that's x plus 4 in the denominator. It allows me to cancel, so that's equal to the limit as x approaches negative 4 of x. So I just do the substitution now, and I can get rid of the limit notation, and that means that is negative 4. And we're going to do the same thing over here for this second one. If I substitute 5 in straight away, I get 0 in the denominator, so we need to factorize. So just a little bit of working out over here. X, two numbers that multiply to give me negative 15 and add to give me negative 2, well, that's going to be negative 5 and plus 3. So this is equal to the limit as x approaches 5 of x minus 5, x plus 3, all over x minus 5, and now I can cancel. So that's equal to the limit as x approaches 5 of x plus 3. That is defined, so I can substitute that in. So I'm going to get 5 plus 3 is equal to 8. And there we are. So real quick refresher. Now, I mentioned this way back here, where technically limit is defined if it's the same value as I approach from the left hand and right hand side. Now we can have different situations where that might not be the case. For example, if we have a hyperbola, okay, if I'm trying to find the limit as x approaches 0 of 1 on x, well, if I'm coming from this positive right-hand side, if I'm coming from more positive x values coming towards 0, well, my y value is approaching infinity. Now, if I come from the other side, if I'm coming from more negative x values, or approaching from the left-hand side, my y value approaches negative infinity. So that limit is not defined at that point. And you can see in this, there's no way I could have factorized that to get rid of the x in the denominator. So the limit doesn't exist at that point, as defined when we just approach whatever from both sides. But what we can do, that's one situation, and the other situation is what happens if we have a piecewise function? What if we have this? This looks like maybe some negative quadratic, translated across as well. It might be something like, who knows, x minus 1 all squared plus 1, something like that. It's not quite right, but could be something like that, quadratic defined up until, so that's x less than or including 1, and then we have a straight line that is also y is equal to just 2 for x greater than 1, and we can see that this function is not joined here. So same thing, if we tried to find the limit as we approach from the left, okay, the limit is 1, but as we approach from the right, coming from the right, we can see that y is, we're getting closer to, even though it's not defined at that point, we're getting closer and closer to 2. So because the limit is not the same at all points, and all we need is one of these spots, or like here where we have a truncus, we have one of these spots where the limit is not the same from both sides. This function is called discontinuous. Or not continuous. Okay. So to be defined, for a function to be defined as continuous, the y value must be the same for any, if we pick any x value, the limit must be the same when we approach from the left and we approach from the right. And if that's not the case, well then technically that function is not continuous, and this will become important in the next exercise when we look at when a function is differentiable, when it is and when it isn't. Okay. Now the notation we use to talk about this, instead of having big written sentences going, if I approach from the left, y gets closer to 1, as I approach from the right, y approaches 2, we use limit notation. And the big thing that we add in is these signs just here. Okay, a little superscript next to the 1, okay, when there's that little negative after it up on the top right, that means we're approaching from more negative values. So as x approaches 1, from more negative values, so that means from the left, okay, that negative 1 there, and then this positive sign means we're approaching x from, we're approaching 1, but from more positive values, so we're coming from the right. Okay, and as we can see, well, the limit on the left-hand side is 1, and the limit on the right-hand side is 2. That's what the y value is getting closer and closer to. And this is the notation we use. We say the limit from the left is 1, the limit from the 2 is right. Sorry, the limit from the left is 1, the limit from the right is 2. Therefore, since they're different, we can say, therefore, the function is discontinuous at x equals -1. So a lot of these checks asking if the function is continuous, it's more looking for, is there any point where it's discontinuous? And then if so, this is the notation we're going to have to write. So let's jump into a couple examples. State the value or values for x for which the function shown has a discontinuity, and use the definition of continuity, blah, to explain why. So there's actually 2 points where this is the situation. We can see as I come from the left, as I approach from the left, I'm getting closer and closer to a y value of 2, but as I approach from the right, my y value is getting closer and closer to negative infinity. We have that asymptote. So we have a discontinuity at that point because the limit as we approach, and that's happening at x equals -1, as we approach we're getting two different values. So the limit as x approaches, and it was x equals -1, and as we approach from the left hand side, f of x, the limit is getting closer to 2, okay, and the limit as x approaches -1 from the right hand side, from more positive values coming in from the right hand side, f of x, we said the limit, the y values are clearly getting closer to negative infinity, therefore f of x is discontinuous at x equals -1. Okay, so there's one point where it's discontinuous. Same here at this other point over here, exactly the same. Now this is happening at x equals +1 as we approach from the left-hand side. As we come up from the left-hand side, we can see that y is equal to 2. But as we come in from the right-hand side, our limit, we're getting closer and closer to y is equal to 3. Doesn't matter that it's not defined at that point. We're thinking we're on a journey. What are we getting closer and closer to? And what could we assume the value to be as we get there? So same thing, the limit as x, in this case, it's approaching +1. But from the left-hand side of f of x, the limit we can see was 2, and the limit as x approached from the right-hand side, so from more positive values, f of x is equal to 3. Same thing, therefore, f of x is, I'm just going to write dis for discontinuous, at x is equal to 1. Just for shorthand. That's not normal notation. I'm just doing it to save time. So we have that right here. So that's exercise 9L. Is 1, just solving some limits, and 2, technically the definition is that it needs to be the same from both sides, and if it's not the same from both sides, then the function has a discontinuity in it, and therefore it means it's discontinuous. Now what does this all mean for derivatives? Well, I'm going to go to this final thing and ignore this title, practice problems. Now, a function is said to be differentiable if our limit, our differentiation via first principles, so this is our first principles equation, okay, because that's where all of differentiation comes from, is that idea of the limit as the gap between those two coordinates approaches 0. That limit needs to exist for all x values on the domain. Now we can get around a lot of this by reducing the domain, but if we're not, or if there is still a break inside that domain, we run into an issue because a limit has to be the same, okay, defined as being the same from the left and the right. So what happens if we run into especially a situation that looks like this, where that's not the case? Where if we've somehow found differentiation via first principles, and this is actually a graph of f dash of x, this is a graph of the gradient, well, what happens at this point here? What is the derivative 2 or is the derivative 3? We don't know. So that's where we run into a really big problem and why we just looked at that previous exercise. So any function is differentiable if the limit as h approaches 0 exists for all x values on the domain. So if we come back, that means, first and foremost, the graph of f of x, and if I do f of x and then f dash of x needs to be continuous. There can't be any gaps, first and foremost. We can't have gaps in the graph, because if I have a graph like that, and that's f of x, Well, what's the derivative of that point? Is it the gradient that's the one on the left? Is it the gradient of the one on the right? We don't know. Okay, so the graph itself, or the function itself, needs to be continuous. Okay, it also means, okay, to be differentiable, it means then the gradient function, so once we find the derivative, that also has to be continuous. We can't have any gaps in that as well, and it needs to be smooth. Okay, because, and I'll show you some examples in a second, of what happens when that's not the case. Actually, no, it doesn't need to be smooth. This one needs to be smooth. Because if the original function is smooth, then it generally implies that f dash of x is continuous. But to sum up, when is a function differentiable? When the original function is continuous, so there's no gaps or breaks in it, and also when f dash of x is continuous, because if it's continuous, then that means the limit is going to exist. As I said, the limit is going to exist for all the required x values. Okay. So let's have a look, and this is almost always going to come up in either an applied problem or a piecewise problem like these down here. That's where it's going to come up. So f of x is equal to x squared minus x minus 2 and x plus 2 for this given domain. Find the derivative. Well, f dash of x is equal to, let's differentiate them individually. That's going to be 2x minus 1, and this is going to be 1. 4x is greater than or equal to 1, and this is 4x less than 1. So that's that. That's easy. There's nothing new here. Let's have a look at the second one as well. F dash of x is going to be equal to negative 2x plus 2, and this is going to be equal to 3. And that's if x is greater than or equal to 0, and if x is less than 0. So let's have a look what this graph looks like. So if I'm going to define, actually let's just go straight into graphing. Keyboard. What do I want? I want a piecewise. No, that's simultaneous. Equation solver. Where's piecewise? Ah, there it is. There we go. Okay, so we've got negative x squared plus 2x plus 3. And I'm showing you this as to provide further context to the problem, but we can do in the next slide, you'll see, doing this without graphing at all or having any idea what the graph of the original equation looks like. X less than 0. Okay, let's graph that. Okay, so straight away graphing this, we can see we've got the linear equation on the left-hand side, and then we've got the inverted quadratic on the right-hand side. They're not connected. So straight away, before we even got to finding the equations of the derivatives or something, looking at that question, we can go, well, that graph's not even connected. So that's not differentiable. And we don't know what the derivative is the left versus the right at that disconnection point. Second thing, okay, is if we then went from that, and if we look at, as I said before, for f of x to have a derivative, okay, or technically be differentiable and defined at all points, f of x needs to be continuous, which clearly on the graph it's not, and f dash of x needs to be continuous. So if we graph this gradient equation, we'll be able to see that it's also not continuous. So for example, we just said before that f dash of x is equal to negative 2x plus 2 and 3. So if we graph the derivative, And this is for x greater than or equal to 0, and that's for x less than 0. So the right-hand side greater than 0, that has a y-intercept of 2, has a gradient of -2, so that's a straight line going down like that. And this is values of x, and this is f dash of x, to clarify. And then the left-hand side is just y is equal to 3 up to that point there. Okay, so same thing we can see here, since we've graphed the derivative and the derivative is not joined at all points, if we tried to find the limit, okay, the limit as h approaches, and in this case h is 0 at, and the break is at x equals 0, well, what's the limit? We don't know from the left, we don't know from the right, so we can't answer this question here at x equals 0. Okay. So state the set of values for which the derivative is defined. Well, the derivative is defined for all real values except at x equals 0. We can't figure out what the derivative is there at that point. Okay, so there's two main ways you can go about answering this question, doing any of the exercise 9M. One is graph the original function. Is it joined? Is it continuous? And are all the joins smooth? So what I mean by smooth is if we had a join like that, and this is f of x, piecewise, that join is not smooth. So again, we don't know what the derivative is at that point. Okay? So we can look purely just at f of x. Is it continuous and is it smooth? Or the other way we can do it is look at f of x, is it joined at all points? And we go, okay, yes, this one is joined at all points. But if I then graph f dash of x, we will also see that the gradient is 0, and then something like that. That would be f dash of x for this graph on the left. We can see the graph of f dash of x is not continuous. So since f dash of x is not continuous, then it's not differentiable at all points. And we will need to restrict it like we just did over here. So that's exercise 9M. So quick review of limits, definition of continuous, and then using that definition to check is a function differentiable at all points. And you will need to use the definition of limits to state that it isn't. If you have any questions, as usual, put it in the comments below or shoot me an email. Thanks and have a good day.